Electrical transformers are devices used to transfer electrical energy between different voltage levels. They are widely used in power transmission and distribution systems, as well as in various electrical and electronic devices. A power transformer is a type of electrical transformer primarily used in power transmission and distribution systems. Its main function is to transfer electrical energy between different voltage levels while maintaining the frequency of the power. Here are some key features and characteristics of power transformers. High power capacity. Power transformers are designed to handle large amounts of power. They are capable of handling power ratings ranging from a few kilovolt amperes, kVA, to several hundred MVA, megavolt amperes. Step up and step down functionality. Power transformers can step up or step down the voltage levels of the electrical energy being transferred. This ability is crucial for efficient power transmission over long distances and for providing appropriate voltage levels to consumers. Core and windings. Power transformers consist of a magnetic core made of laminated iron or steel sheets. The core reduces energy losses and provides a path for the magnetic flux generated by the primary and secondary windings. The windings are insulated copper or aluminum conductors wound around the core and connected to the primary and secondary power systems. Cooling systems. Power transformers generate heat during operation, and cooling systems are employed to dissipate this heat. Common cooling methods include natural air cooling, forced air cooling, oil cooling, using oil as a coolant and insulator, and water cooling for very large transformers. Tap changers. Power transformers may include tap changers, which are mechanisms that allow for adjusting the turns ratio and output voltage level. Tap changers help compensate for voltage fluctuations in the power system and enable voltage regulation. High voltage and current ratings. Power transformers are designed to withstand high voltages and currents commonly encountered in power transmission and distribution systems. They have robust insulation systems and are built to handle the stresses of these high-power environments. Efficiency and losses. Power transformers aim to achieve high efficiency in transferring electrical energy, with minimal power losses. Efforts are made to minimize core losses, hysteresis and eddy current losses, and copper losses, resistive losses in the windings. A distribution transformer is a type of electrical transformer that is used to step down the voltage from the primary distribution level to the secondary distribution level. Its primary function is to distribute electrical power from the main transmission lines to the end users, such as residential, commercial, and industrial consumers. Here are some key features and characteristics of distribution transformers. Voltage regulation. Distribution transformers typically step down the high voltage power received from the transmission system to lower voltage levels suitable for local distribution. The primary voltage can range from a few kilovolts, kV, to tens of kilovolts, while the secondary voltage is typically in the range of a few hundred volts to a few kilovolts. Single-phase and three-phase. Distribution transformers are available in both single-phase and three-phase configurations, depending on the power demand and the type of electrical system in use. Single-phase transformers are commonly used in residential applications, while three-phase transformers are employed in commercial and industrial settings. Core and windings. Distribution transformers have a laminated iron or steel core and two sets of windings, the primary winding and the secondary winding. The core provides a path for the magnetic flux generated by the windings and helps reduce energy losses. The windings are made of insulated copper or aluminum conductors and are connected to the primary and secondary power systems. Oil immersion. Distribution transformers are often oil immersed, where the windings and core are immersed in a high-quality insulating oil, such as mineral oil. The oil serves both as a coolant and an insulator, helping dissipate heat generated during operation and providing electrical insulation. Bushings and terminals. Distribution transformers are equipped with bushings and terminals for the connection of power lines. Bushings are insulated devices that allow electrical connections to be made between the transformer and the primary and secondary power systems. Terminals provide access points for electrical connections to the transformer. Efficiency and losses. Distribution transformers aim to achieve high efficiency in power conversion, minimizing power losses in the form of core losses and copper losses in the windings. Efforts are made to optimize the design and materials used to reduce these losses and increase overall efficiency. Compact and pad-mounted designs. Distribution transformers come in various sizes and designs to suit different installation requirements. Compact transformers are commonly used for urban and densely populated areas where space is limited. Pad-mounted transformers are designed to be installed on concrete pads or metal platforms outdoors, providing easy access for maintenance and reducing the impact on the surrounding environment. Distribution transformers are crucial components of the electrical distribution system, facilitating the safe and efficient delivery of electrical power to consumers. They play a vital role in maintaining voltage levels, reducing the risk of power disruptions, and ensuring a reliable supply of electricity to homes, businesses, and industries. Instrument transformers are specialized transformers used in electrical systems to measure and monitor high voltage and current levels accurately. They are essential for the safe and efficient operation of power systems and for providing reliable measurements to various instruments and protective devices. There are two main types of instrument transformers: current transformers and potential transformers, also known as voltage transformers. Here's an overview of each type. Current transformers, CTs. Current transformers are designed to step down high primary currents to a proportional secondary current that is suitable for measurement or protection devices. The primary winding of a CT is connected in series with the power circuit, allowing it to carry the actual current. The secondary winding is connected to measuring instruments, relays, or meters. Key features of current transformers include accuracy. CTs are highly accurate devices, designed to provide precise measurements of current levels. Burden. CTs have a burden, which is the maximum current that can be delivered to the secondary circuit without affecting accuracy. Turns ratio. The turns ratio of a current transformer determines the ratio between the primary current and the secondary current. Potential transformers, or voltage transformers, are used to step down high primary voltages to a lower proportional secondary voltage suitable for measurement or protection devices. PTs are connected in parallel to the power circuit, and the secondary winding provides an accurately scaled down voltage that represents the primary voltage. Key features of potential transformers include accuracy. PTs provide accurate voltage measurements and are designed to minimize errors in voltage measurement. Turns ratio. The turns ratio of a potential transformer determines the ratio between the primary voltage and the secondary voltage. Burden. PTs have a burden, which is the maximum load that can be connected to the secondary winding without affecting accuracy. Both current transformers and potential transformers are typically used in conjunction with various instruments, meters, relays, and protective devices in electrical systems. They ensure that accurate and scaled-down measurements of current and voltage levels are available for monitoring, control, and protection purposes. These instrument transformers are crucial components for system analysis, power quality monitoring, revenue metering, and overall system reliability. An autotransformer is a type of electrical transformer that has a single winding with multiple taps, allowing it to function as both a step-up and a step-down transformer. It differs from a conventional transformer, which has separate primary and secondary windings. In an autotransformer, a portion of the winding serves as both the primary and secondary winding. Here are some key features and uses of autotransformers. Voltage conversion. The primary function of an autotransformer is to provide voltage conversion. By connecting the load to different taps on the winding, the autotransformer can step up or step down the voltage to the desired level. Lower size and weight. Autotransformers are generally smaller and lighter than conventional transformers with similar power ratings. This is because they share a common winding for both the primary and secondary, reducing the amount of copper and iron required. Variable voltage output. Autotransformers offer the advantage of providing variable voltage output by utilizing multiple taps on the winding. This makes them suitable for applications where voltage adjustment is necessary, such as laboratory equipment, testing setups, or industrial processes. Efficiency. Autotransformers generally have higher efficiency compared to conventional transformers. This is due to reduced copper and core losses resulting from the shared winding. Cost savings. The use of autotransformers can lead to cost savings in terms of reduced material requirements and lower overall manufacturing costs compared to conventional transformers. Applications. Autotransformers find applications in various areas, including voltage regulation, motor starting, control systems, and audio systems. They are commonly used in industries where voltage adjustment is required for specific equipment or processes. It's worth noting that autotransformers have some limitations. Since the primary and secondary windings are not electrically isolated, there is a direct electrical connection between them. This means that any fault or short circuit in the winding can result in a direct transfer of high voltage or current. Therefore, proper precautions and protective measures should be implemented when using autotransformers to ensure safe operation. Isolation transformers are a type of electrical transformer specifically designed to provide electrical isolation between the input and output windings. They offer galvanic isolation, which means there is no direct electrical connection between the primary and secondary windings. Instead, they are magnetically coupled through a transformer core. Here are some key features and uses of isolation transformers. Electrical isolation. The primary purpose of an isolation transformer is to electrically isolate the input and output circuits. This isolation helps protect sensitive equipment or devices from electrical noise, voltage spikes, transients, and ground potential differences. It also enhances safety by eliminating the risk of electrical shock due to direct contact with the primary circuit. Noise reduction. Isolation transformers provide a barrier against electrical noise and interference that can be induced on the power line. They block high-frequency noise and transients from propagating to the output side, ensuring cleaner and more reliable power for connected equipment. Voltage regulation. Isolation transformers can also provide voltage regulation by compensating for voltage fluctuations or variations in the input power supply. They maintain a stable output voltage, which is crucial for sensitive electronic equipment that requires a consistent power supply. Ground isolation. Isolation transformers can effectively separate the grounding systems of the input and output circuits. This can be beneficial in situations where different ground references exist or where grounding issues may cause ground loops or other problems. Ground isolation helps prevent current flow through ground connections, minimizing noise and improving system performance. Safety applications. Isolation transformers are commonly used in medical facilities and laboratories where electrical equipment needs to be isolated from the main power supply. They provide an additional layer of safety by protecting patients, operators, and sensitive equipment from electrical faults and surges. Power conditioning. Isolation transformers can help in conditioning the power supply by removing common mode noise and harmonics. This can improve the performance and reliability of connected devices, especially in audio, video applications or critical data centers. UPS systems. Uninterruptible power supply, UPS, systems often incorporate isolation transformers to provide isolation and enhanced protection for critical loads. The isolation transformer can serve as an additional layer of defense against power disturbances and faults, ensuring uninterrupted power supply to the connected equipment. Isolation transformers are available in various power ratings and configurations to suit different applications. They are particularly valuable in situations where electrical isolation, noise reduction, voltage regulation, and enhanced safety are essential requirements. Ferroresonant transformers, also known as constant voltage transformers, CVTs, or ferroresonant regulators, FRRs, are a type of specialized transformer that provides voltage regulation and isolation. They use a combination of magnetic saturation and resonant circuitry to maintain a relatively constant output voltage despite fluctuations in the input voltage. Here are some key features and characteristics of ferroresonant transformers. Voltage regulation. Ferroresonant transformers are designed to provide a nearly constant output voltage, even when the input voltage varies within a certain range. This makes them suitable for applications where a stable and regulated voltage supply is required. Magnetic saturation. Ferroresonant transformers utilize a magnetic core made of a material that exhibits nonlinear magnetization characteristics. When the core approaches saturation, it helps maintain a stable output voltage, regardless of input voltage variations. Resonant circuit. Ferroresonant transformers incorporate a resonant circuit, typically consisting of capacitors and inductors, which is connected in parallel to the output winding. The resonant circuit forms a voltage divider, ensuring that the output voltage remains relatively constant. Voltage regulation range. Ferroresonant transformers have a specific input voltage regulation range within which the output voltage remains constant. They are typically designed to maintain a constant output voltage within a range of plus or minus 10% to plus or minus 20% of the nominal input voltage. Limited overload capacity. Ferroresonant transformers have a limited ability to handle overload conditions. They can withstand short-duration overload currents but are not suitable for continuous or sustained overload conditions. Exceeding the overload capacity can lead to saturation of the core and result in output voltage variations. Isolation and transient protection. Ferroresonant transformers provide electrical isolation between the input and output windings, offering protection against electrical noise, transients, and voltage spikes. Applications. Ferroresonant transformers are commonly used in applications where a regulated voltage supply is critical, such as in sensitive electronic equipment, telecommunication systems, data centers, and computer networks. They are also employed in areas with unreliable or fluctuating power supplies, providing a stable voltage output to protect connected equipment. Pulse transformers are specialized transformers designed to handle and transmit electrical pulses with fast rise and fall times. They are commonly used in applications involving high-speed digital communication, data transmission, pulse power systems, and in various electronics and telecommunications equipment. Here are some key features and characteristics of pulse transformers. Wide bandwidth. Pulse transformers are designed to operate over a wide frequency range, allowing them to handle fast-rising and fast-falling electrical pulses. They are capable of transmitting high-frequency signals without significant distortion. High voltage isolation. Pulse transformers provide electrical isolation between the input and output circuits, which is crucial for safety and protection. The insulation is designed to withstand the high voltages associated with pulse applications, preventing electrical breakdown and ensuring reliable operation. Impedance matching. Pulse transformers are often used for impedance matching between the driving and receiving circuits. They help maximize the transfer of energy between these circuits by matching the impedance of the source and load, optimizing the signal transmission. Compact size. Pulse transformers are typically designed to be compact and lightweight, making them suitable for integration into small electronic devices and circuit boards. Core material. Pulse transformers may utilize various core materials, including ferrite, powdered iron, or other materials with high permeability and low losses. The choice of core material depends on the specific application requirements, including frequency range, power handling, and desired electrical characteristics. Turns ratio. The turns ratio of a pulse transformer determines the voltage transformation between the primary and secondary windings. By selecting an appropriate turns ratio, the pulse transformer can step up or step down the voltage levels as needed for the application. Pulse shaping. Pulse transformers can be used for pulse shaping and pulse modulation. By carefully designing the winding configuration and core characteristics, pulse transformers can shape the rise and fall times of the pulses, reduce ringing and overshoot, and improve the overall signal quality. Application examples. Pulse transformers find applications in various fields, including telecommunications, data communications, pulse power systems, high-speed digital circuits, radar systems, pulse generators, and power electronics. Toroidal transformers are a type of electrical transformer that features a toroidal, donut-shaped, core. The core is typically made of a ferromagnetic material, such as iron powder or laminated silicon steel, and it provides a closed magnetic circuit for efficient energy transfer.